Welcome to Grandpa's Late Nights. Come in, kiddo. Pull the blanket up a little higher, settle your head into the pillow just the way you like it. I've got the porch light on, same as always, and the house is quiet now, and there's nowhere you need to be, and nothing you need to do but rest. So let's just be here together for a while, you and me, while the night gets long and soft around us. Wherever you are tonight, and I do wonder where that is, and I hope you're warm. Maybe you're tucked into your own bed in a house I'll never see, in a town I'll never visit. Maybe you're on a couch with the lamp still glowing in the corner, or riding home late on a train that rocks you a little with every turn of the track. Maybe it's raining where you are, maybe it's the middle of the afternoon, and you just need somewhere quiet to put your mind down for a while. It doesn't matter to me which it is. I'm just glad you came by. And if you'd like to tell me, sometime, where in the world you're listening from tonight, and what hour it is in your corner of the dark, well, I'd love to know that. It makes this old porch feel a little less empty. Now, before we get going, let me say one small thing and then I'll hush about it. If you find you like these slow nights of ours, a little tap to like, a little tap to subscribe. It genuinely helps this sleepy little channel keep its lights on. Small folks like me lean on that more than you'd think. And to those of you who've already done it, who keep coming back night after night, thank you truly. You're the reason the porch light stays on. There. That's done. I won't bring it up again until the end. Here's the other thing I want you to know before we start. And it's the most important thing, so listen close even as your eyes get heavy. You do not have to follow every word of this. You don't have to understand all of it. You don't even have to stay awake for it. If you drift off somewhere in the middle, that is exactly perfectly fine. That's what this is for. The ideas will still be here when you wake. They're patient things, ideas. They don't mind waiting. So let your shoulders drop. Let your jaw unclench. Let the worries of the day go soft and far away, like lights on a hill seen from a moving car. We're going to take this slow tonight, as slow as falling snow. I'd say I'll try not to make it so interesting it keeps you awake, but if it does, well, at least you'll have learned something lovely. That's a fair trade, I think. So, settle in. Let me tell you a strange and beautiful thing. There is, somewhere out in the dark, another you, not someone a little like you, not a person who reminds you of yourself the way a cousin might, or an old photograph of your father at your age. I mean another you, someone made of the very same arrangement of atoms, down to the last one. Someone with your exact face, your exact hands, the same small scar in the same small place. Someone whose mind holds your every memory, the good ones and the ones you'd rather forget, laid out in precisely the same way yours are laid out, like books on a shelf in the same crooked order. There may be a version of you far out in the dark, lying in a bed just like yours, hearing a voice just like mine, drifting towards sleep at this very moment, just as you are now. And tonight, slowly, gently, I want to tell you how serious people came to believe that, and how far away that other you would have to be. Because there's a number for it, a real one, and it is one of the strangest numbers a human being has ever written down. Let me give it to you, and then we'll spend the whole night unwrapping it, like a present we're in no hurry to open all at once. The distance to the nearest exact copy of you is about 10 to the power of 10 to the power of 28 meters. Now I know that's a mouthful, and your sleepy mind probably just let it slide right past, and that's all right. Let me say it again, slower, and let me tell you what makes it so peculiar. It's not 10 with 28 zeros after it. It's a tower of numbers. It's 10 raised to a number that is itself 10 raised to 28. Think of it as a number so large that even the count of its digits is enormous. The number of zeros you'd have to write, just the zeros, is itself a 10, followed by 28 more zeros. You could not write this number down, not on paper, not on every page of every book ever printed, not if you covered every wall in the world with tiny digits. It is, in the plainest sense, beyond writing. But here's the part that I find truly wonderful, the part that breaks something gently in your head and lets the wonder in. Here it is. Are you ready? It doesn't matter what units you measure it in. Let me say that again because it sounds like nonsense the first time, and it isn't. Whether you measure that distance in meters or in miles or in light years, the great long stretch a beam of light travels in a whole year, or in the very smallest length that physics even talks about, a length so tiny it makes an atom look like a galaxy, the answer comes out the same. Now stop and feel how odd that is. In your everyday life, the unit is everything, isn't it? The distance to the corner store is a very different number in inches than it is in miles. A trip across the country is a small number if you count it in days, and a big, frightening number if you count it in footsteps. The ruler you choose changes the answer. That's how the world has always worked for you. That's how it works for everything you have ever measured in your whole life. But not here. Not at this scale. Out here, at the distance to the other you could switch from inches to light years, a leap of unimaginable size, multiplying or dividing by trillions upon trillions, and the number barely flinches. The change happens way down at the very bottom of that tower of powers, in a spot so deep and so swamped by everything stacked on top of it that the whole adjustment simply vanishes. It gets lost. The number is so vast that the choice of ruler stops mattering. Inches or light years, it's the same answer. I don't know about you, but the first time I really sat with that, I had to put down what I was doing and just breathe for a minute. Because we are so used to thinking that bigness is just more of the same. More zeros, a longer number, a heavier weight. And here is a kind of bigness so different in character that it eats the very idea of a measuring stick. It's not just far. It's far in a way that makes far stop meaning what you thought it meant. So hold on to that, tuck it under your pillow, we'll come back to it. Now you might be lying there thinking, and it would be a very fair thing to think, all right, that's a lovely big number, but how on earth could anyone know that? How could anyone possibly claim there's another me out in the dark? Isn't that just a story? Isn't that just somebody dreaming? And here is where I have to be honest with you. The way I'd always be honest with you, because I think you deserve that even half asleep. Maybe especially half asleep, when your guard is down and you can hear things true. This whole beautiful idea, the other you, the number, all of it, it balances on a single word, and that word is if. If the universe is truly infinite, if space goes on and on without ever ending, forever in every direction, then the other you is not a guess. It is not a maybe. It is very nearly a guarantee. It follows the way 2 and 2 follow into 4. It becomes something almost like a theorem, a thing proven, a thing that simply must be so. But that little word, if, that's the whole trouble. Because we do not actually know whether the universe is infinite. We can't see far enough to tell. We may never be able to tell. So what we have, kiddo, is something I think of as a seesaw. On one end, an almost certainty, a conclusion so tight and clean it feels like arithmetic. And on the other end, holding it all up, a great big maybe, an almost theorem resting on a maybe. That's the strange and honest shape of this thing, and I think it's more beautiful that way, not less. A wonder with a question mark folded inside it. We're going to spend tonight on both ends of that seesaw. I'll show you why, if the if holds, the other you is practically forced to exist. I'll make that logic so simple and so clean that you'll feel it click into place like a key in a lock. And then I'll turn around and show you just as carefully why that if is so very hard to settle and why some of the smartest people alive disagree about it to this day. By the end, I hope you'll feel both things at once, the gentle chill of the guarantee and the soft vertigo of the doubt. And then I hope you'll be fast asleep and you can carry both of them down into your dreams. But first, before we can talk sensibly about infinite space, I need to clear away a misunderstanding. It's a very common one. Almost everybody carries it around without realizing, and it gets in the way of seeing this clearly. So let's set it gently aside together. When you think of the Big Bang, the beginning of everything, the start of the universe, what picture comes to mind? I'd wager it's something like an explosion, a single tiny point, a speck, sitting in the middle of an empty blackness, and then, bang, it bursts outward, flinging matter in all directions, filling up the emptiness around it, a firework in a dark sky. That's the picture most of us were handed somewhere along the way. And it's wrong, gently but genuinely wrong. And once you let it go, a great many puzzling things suddenly make sense, including how the universe could be infinite right now. The Big Bang was not an explosion from a point into empty space. There was no empty space around it for things to fly into. The space is the thing that was hot and dense. Let me say that more carefully. In the beginning, everything, all of space itself, was packed close and unbearably hot. Not a small ball of matter sitting in a big empty room. The room itself was the small hot thing. And then space began to stretch everywhere all at once, not exploding outward from a center because there was no center. There was no edge to be at the center of. Every place was, in a sense, the middle. Every place was already there. Here's a homely way to picture it. The kind of thing you can hold in a sleepy mind. Imagine a loaf of raisin bread dough sitting in a warm kitchen beginning to rise. The raisins are galaxies. As the dough swells, every raisin drifts away from every other raisin. Pick any raisin and look around from it, and you'll see all the others moving off. And so it looks from that raisin as if it's the center, as if everything is fleeing from it. But it isn't the center. No raisin is. They all see the same thing. The dough is just getting bigger everywhere, all together. There's no edge in the middle of the loaf where the rising started. It started everywhere. Now here's the leap, and it's a soft one, so go with me. Imagine that loaf has no crust. Imagine it goes on forever in every direction. An infinite loaf of raisin bread, already infinite, full of infinitely many raisins, and then it begins to rise. The rising still happens everywhere. Every raisin still drifts from every other. There's still no center and no edge. The whole infinite thing just gets more spread out, less dense, cooler. That's a universe that was infinite at the start and is infinite now. The Big Bang, if the universe is infinite, happened everywhere in an already infinite space. It was not a small thing that grew into a big empty room. It was an infinite thing that got less crowded. The hot, dense beginning was hot and dense everywhere, all across an endless expanse, all at the same instant. So you see, there's no contradiction in saying the universe is only about 13.8 billion years old, young really, as these things go, and also saying it might be infinitely large. Age and size are two different questions. The universe can be a certain number of years old and still stretch on without end because it didn't have to grow out from a point to reach that size. It could have been endless from its very first moment. Let that settle. It's a quiet thing, but it changes the whole shape of what's possible. Once you stop imagining a firework in the dark and start imagining an endless loaf gently rising, the idea of infinite space stops feeling like a paradox and starts feeling like just one of the ways things might be. Now, I've been saying infinite And I've been saying the universe. And I want to be very careful with you here because there's a second thing people tangle up. And untangling it is going to matter a great deal later tonight. Stay with me just a little longer, and then I promise we'll rest in it for a while. There is the universe, the whole of it, however big or small it truly is, whether finite or endless, all of it. And then there is something smaller, something with a name, something we can actually talk about with real numbers. It's called the observable universe. And the observable universe is not infinite, it is finite. It has a size, we can put a number on it. Here's why. Light travels fast, faster than anything, but it does not travel infinitely fast. It takes time to get from there to here. When you look up at a star, you're not seeing the star as it is now. You're seeing the light that left it long ago, finally arriving at your eye. Look at something 100 light years away, and you're seeing it as it was 100 years past. The farther out you look, the deeper into the past you're peering. Light is a slow messenger from far places, and the message is always old by the time it reaches you. And here's the catch. The universe has only been around for about 13.8 billion years, so there simply hasn't been enough time since the beginning for light from very, very distant places to reach us yet. Beyond a certain distance, the light just hasn't had time to arrive. It's still on its way, or it'll never make it at all. There's a horizon like the horizon at sea, the line beyond which you cannot see, not because the ocean ends there, but because the curve of things hides the rest. Our cosmic horizon hides the rest of the universe behind the simple fact that light is slow and time is short. So the observable universe is a sphere, a great ball, with us sitting right at the center of it. Not because we're special, mind you, but because each of us is always at the center of our own seeing, the way you're always at the center of how far you can see across a foggy field. Everyone, everywhere, sits at the center of their own observable universe. Yours is centered on you tonight, in your bed. Now you might think that sphere would have a radius of about 13.8 billion light years. 1 light year for every year the light's been traveling. But it's bigger than that. Quite a lot bigger. The radius of the observable universe is about 46.5 billion light years. And isn't that a funny thing? How can we see something 46 billion light years away if light has only had 13 billion years to travel? It seems like the light would have had to go faster than light to get here, which nothing can do. The answer is that lovely, patient idea we talked about a moment ago. Space itself stretches. While that ancient light was creeping toward us across the ages, the space it was crossing was swelling underneath it, the whole way, like a moving walkway carrying it along, or like that rising dough lifting every raisin apart. The light set out from a place that was much closer back then. But by the time it reached us, the place it started from had been carried far, far away by the expansion. So the distance to it now, where it sits today, stretched out across all those billions of years of swelling space, is about 46.5 billion light years, even though the light itself only traveled for 13.8 billion of them. The light didn't break any rules, the road just kept getting longer beneath its feet. This sphere, this ball of everything we could possibly see, 46.5 billion light years out in every direction, has a few different names, and I'll give them to you so they don't startle you if you hear them later. Some folks call it the Hubble volume. Some call it the particle horizon being the very edge of it, the boundary line past which no particle, no speck of light, has had time to reach us. It's all the same idea, dressed in different words. The patch of everything we can see, finite, measurable, ours. And here is the quiet thing I want you to carry into the next part of our night, the seed of everything that follows. The observable universe is finite, we know that. But the whole universe, all of it, beyond our horizon, past the edge of our seeing, that might go on forever. There might be endless more space out there, endless more of those 46 billion light-year spheres stacked side by side in every direction, an ocean of them with no shore. We can't see them, we can never see them, the light from them will never reach us. But they might be there, sphere after sphere after sphere, on and on, without end. And if they are, if there truly are infinitely many of those great spheres out in the dark, then something remarkable is forced to happen inside them. Something that brings us all the way back to the other you, lying in a bed just like yours, somewhere unimaginably far away. But that's where the real machinery is. That's the engine of the whole strange idea. Why infinitely many spheres must contain a copy of you. And it's a beautiful piece of reasoning, simple enough that a child could follow it, and deep enough that it troubles the wisest minds we have. I want to give it to you slowly, with all the care it deserves. So rest here a moment first. We've come a little way already tonight, you and I. We've held a number so large it laughs at rulers. We've set down the old firework picture of the Big Bang and picked up the gentler one, the endless loaf, rising everywhere at once, no center, no edge. We've drawn the boundary of all we can see, 46.5 billion light-years out, and given it its names. And we've found the seed of the whole mystery sitting just past that boundary in the dark we cannot reach. There's no rush. Your breathing's gone slower, I can tell, and that's just right. If you're already halfway to sleep, then let yourself go the rest of the way, and I'll keep talking soft out here on the porch. And the ideas will wait for you, patient as ever. But if you're still with me, still curious, still wanting to know how on earth infinitely many spheres can guarantee another you, then stay a little longer. Because next, I'm going to tell you about a principle so simple it sounds like a children's game, about pigeons and the little boxes they roost in. And I'm going to show you how that humble little rule, when you stretch it across an endless universe, quietly forces the existence of someone exactly like you, out there in the dark, breathing in time with you now. But before the pigeons, let me circle back to that number one more time, because I don't think it landed yet. Not really, not the way it should. Numbers this big, your mind just slides off them. It hears very far and files it next to the moon, next to the edge of the galaxy, and moves on. So let me try to make it stick. The nearest exact you sits about 10 to the 10 to the 28 meters away. Say it slow, 10 raised to a power, and that power is itself 10 raised to 28. A tower of numbers stacked on numbers. Not a big number, a number about big numbers. The amount of digits you'd have to write just to spell it out is itself a number with 28 digits in it. You could write zeros from now until you fell asleep, and again tomorrow night, and every night for the rest of your life, and you would not come close to finishing the address of the other you. And here's the part that I find quietly astonishing, the part I keep turning over like a smooth stone in my pocket. The units don't matter, they simply don't. Think about what that means for a second. Picture a distance. Any ordinary distance. The length of your bed. If I measure it in inches, I get one number. In feet, a smaller one. In miles, smaller still. The ruler I pick changes the answer. That's how measuring works. That's how it's always worked, since the first person paced off a field. A light year is about 10 trillion kilometers, a stupendous stretch. The distance light crawls in a year, and light is the fastest thing there is. You'd think swapping meters for light years would shrink our number enormously, shave whole mountains off it. It doesn't, it barely scratches it, because all that swap does is nudge the very bottom of the tower by a sliver, by a few dozen, and a few dozen against 10 to the 28 is nothing, less than nothing. It's a single grain of sand dropped into an ocean that has no shore. Measure the distance to your copy in meters, in light years, in inches, in the width of a single atom, in the tiniest length, physics even allows. And you get the same answer, the same tower. The choice of ruler, the thing that has always mattered when we measure the world, here simply ceases to mean anything at all. I don't know a gentler way to say how strange that is. We have finally reached a distance so large that the very idea of how you measure dissolves. The question loses its grip. That's not a number you can picture. It's a number that quietly retires your ability to picture and hands you wonder instead. So just let that sit there, glowing softly, while I tell you where the whole thing leans. Because here's the shape of tonight's story, the real spine of it, and I want you to hold it loosely in your mind like a thread you can follow even in the dark. Everything I'm building toward, the guaranteed copy, the infinite roosting spheres, the someone just like you, out past the edge. All of it stands on one foot. It's almost a theorem, you see. The logic, once you accept the starting line, is so tight it barely leaves room to wriggle. Given the premise, the other you doesn't merely become likely. With infinitely many tries and a fixed, honest chance on each one, the probability isn't 99%, isn't 99.9. It's 1. Certainty. Not there's probably a copy. There is a copy, and not one, endlessly many, recurring forever out into the dark. That's the theorem half, cold, clean, almost unarguable. But it rests on a maybe. The whole gleaming structure balances on a single small word, and the word is if. If space goes on forever. That's the foot it stands on. Pull that word, and the whole thing folds up like a paper bird. And the trouble, the beautiful, maddening trouble we'll come to before the night is through, is that nobody knows if it's true. It may be a thing we can never know, almost a theorem, resting on a maybe. Hold that. It's the heart of everything. Now, before we go further, I have to clear away one stubborn little weed, because if I don't, the whole idea of infinite space right now will sound like nonsense, and it isn't. It's the misunderstanding nearly everyone carries about the Big Bang, and I carried it too for the longest time. You've heard the story, surely? In the beginning, everything was crammed into a single point, smaller than a pinhead, infinitely dense, and then, bang, it exploded outward into the empty, waiting dark. And that explosion is the universe, still flying apart even now. It's a vivid picture, it's on every documentary. And it's wrong, not a little wrong. Wrong in the way that matters most for tonight. The Big Bang was not an explosion at a place. There was no place for it to happen at. The Big Bang happened everywhere, all at once, everywhere there is. Let me say it another way softly, because it's worth getting right. Go back to our loaf of bread, the one rising in the warm dark of the oven, raisins drifting apart as the dough swells. Now imagine the dough was never small. Imagine it was already infinite, already stretching out forever in every direction. And what the Big Bang describes is not a point bursting open, but that entire endless dough, all of it, everywhere at once, suddenly hot and dense and beginning to rise. The early universe wasn't a tiny speck sitting in emptiness. It was infinite space everywhere, full to the brim and blazing. So the bang didn't happen over there in some particular corner, with the rest of space waiting empty to be filled. It happened here. It happened where you're lying right now. And it happened at the same instant, a billion light years away, and a billion past that, on and on, with no far wall to stop it. The whole of space was already there, and all of it lit up together. And once you see it that way, the puzzle that's probably been nagging at you just quietly unknots itself. How can the universe be infinite now if it's only 13.8 billion years old? How did it get infinitely big in finite time? And the answer is that it didn't have to get infinitely big. It was already infinitely big. There was never a moment when infinite space had to be assembled out of a point, because there was never a point. If space is endless today, then it was endless in its very first second, just hotter, just denser, just closer packed. Infinity all along. That's the thing the old firework picture quietly steals from you, and I wanted to hand it back. A universe that is infinite right now isn't a paradox, it's perfectly coherent. The dough was always endless, it only just began to rise. Now, and this matters, so stay with me one more breath. None of that means we can see the infinite part. We can't. We never could. This is the boundary we drew a little while ago, and I want to set it firmly in place before we go on, because everything tonight lives on one side of it or the other. What we can see is a sphere, a single, finite sphere, with us sitting at the very center of it, the way you always sit at the center of how far you can see on a foggy night. The light from beyond a certain distance simply hasn't had time to reach us yet, not in the whole life of the universe. And so that distance is a wall. Not a wall of brick, but a wall of waiting. The farthest light we'll ever catch sets the edge. That edge has a radius of about 46.5 billion light years. I know I said the universe is only 13.8 billion years old, and now I'm telling you we can see things 46 billion light years out, more than 3 times farther than light should have been able to travel. It sounds like cheating. It isn't. It's just that while the light was patiently crossing toward us, the space it was crossing kept stretching underneath it, carrying the source ever farther away, like a swimmer pushing forward along a river that keeps lengthening beneath them. So the place that sent us that ancient light is, by now, far more distant than the simple journey of the light would suggest. That sphere has names, sober and useful ones. Some call it the observable universe, plain enough. Some call it the Hubble volume. The most careful name is the particle horizon. The horizon set by how far any particle of light could possibly have traveled to reach us since the beginning, all the same line drawn in the dark, marking the limit of everything we will ever see. And here is the quiet, enormous thing. That sphere is finite, we've measured it, we know its size, but the universe it sits inside, or that may go on forever, sphere after sphere after sphere, each one a world entire, all of them out past our horizon, in the dark we can never reach. So let's think about what it actually means for something to repeat. Not repeat like a chorus in a song or a face you keep seeing in a crowd. Repeat in the deepest, most mechanical sense, the way a finite set of options, given enough room, is forced to cycle back on itself. There's a mathematical principle at work here, so old and so simple that children encounter it in school and then spend the rest of their lives not quite appreciating how radical it really is. And right now, at the edge of everything we know about the cosmos, it's doing something astonishing. It's called the pigeonhole principle. You've probably met it without knowing the name. The idea is this: if you have more pigeons than pigeonholes, then at least one pigeonhole must hold more than one pigeon. That's it. That's the whole thing. It sounds like a trivial observation about birds and carpentry, and it is, and it's also one of the most quietly powerful ideas in all of mathematics. It means that when the number of things exceeds the number of possible places for them, repetition isn't optional. It isn't lucky. It's enforced by counting alone with no exceptions. Now here is what happens when you carry that principle out of the schoolroom and into the cosmos. Imagine, and we'll do this very slowly because the image is worth building carefully, imagine the observable universe as a box. Your box. The sphere we talked about, 46.5 billion light years in every direction, a bubble of space centered on you with everything we could ever possibly observe sitting inside it. Your entire slice of the cosmic story sealed at the horizon. Now imagine that box can only be arranged in a finite number of ways, not infinite ways. A very, very large number of ways, incomprehensibly large, in fact, but finite. A number that has an end, even if writing down that end would require more paper than exists anywhere in the universe. Finite. Countable, at least in principle. And now imagine there are infinitely many such boxes stretching out past your horizon, on and on without stopping, each one drawn from that same set of possible arrangements. The pigeonhole principle wakes up. If the number of boxes is infinite and the number of possible contents is merely finite, then at least one content must appear in more than one box. In fact, every possible content appears in infinitely many boxes. No arrangement gets left out. No arrangement appears only once. Every configuration of matter, every possible state, recurs endlessly across the infinite expanse because it simply has no other choice. Infinity divided by any finite number is still infinity. Your nearest exact copy isn't a possibility, it's an inevitability. But, and this is what we should linger on for a moment because it's easy to slide past it, this argument has a load-bearing beam in the middle of it. The beam is the claim that the contents of one of those boxes can only be arranged in finitely many ways. Take that away and the pigeonhole engine stalls. So where does that claim come from? Why should any region of space, no matter how enormous, have a limited number of possible states? Space looks continuous to us. Matter looks infinitely divisible, infinitely adjustable. Why shouldn't there be infinitely many possible arrangements inside any given bubble of the cosmos? The answer comes from some of the most profound and hard-won physics of the 20th century. And the man who first made it rigorous, who gave it a name and an equation, was a physicist named Jakob Bekenstein. The year was 1981, though the groundwork had been laid a decade earlier, in the strange overlap between general relativity and thermodynamics. Bekenstein had been thinking about black holes, which are, in a very real sense, the universe's filing cabinets, places where matter and information go to be compressed. And he noticed something that at first looked like a bookkeeping puzzle and turned out to be a statement about the fundamental nature of reality. He noticed that the amount of information a black hole could contain seemed to be proportional not to its volume, but to its surface area. The space inside wasn't the relevant measure. The boundary was. And if that was true for black holes, which are the most extreme objects in the universe, perhaps it was true more generally. Perhaps any region of space, any region at all, had a maximum amount of information it could contain, set by the area of its boundary, not the volume inside it. This became known as the Bekenstein bound. Think of it this way. You have a room. Common sense says the amount of stuff you can put in the room is determined by how big the room is. Its volume, its 3 dimensions of space. More room, more stuff. Straightforward. But the Bekenstein bound says something stranger. It says the maximum information content of what's inside that room is determined by the area of the walls around it, the 2-dimensional skin of the room, not the 3-dimensional interior. As if the room's walls are a screen and everything inside is a kind of projection of what's written on that screen. This is the holographic principle, and it was developed further by Gerard 't Hooft, the Dutch physicist, and Leonard Susskind, the American physicist, who became one of its most eloquent champions. The name is evocative and deliberate. A hologram is a flat, 2-dimensional surface that encodes a 3-dimensional image. The holographic principle suggests that in some deep and possibly literal sense, the universe works the same way. That 3-dimensional reality is, at its roots, encoded on a 2-dimensional surface, and that the information content of any region is fundamentally bounded by that surface. It's a strange and almost vertiginous idea. We won't need to fully grasp it. There's no need to grasp every equation tonight. And if you're already drifting a little, that's fine. The ideas will still be here. But what matters for us right now is the consequence. The consequence is this. A Hubble volume, your bubble, 46.5 billion light-years in radius, contains a finite amount of information. Not unlimited, not continuous. Finite, granular, bounded by the physics of the horizon that wraps around it. The universe at the deepest level is not infinitely detailed, it's made of bits. A staggering number of bits, but a number, a specific number, with a value that Tegmark and others have tried to estimate. The number of distinct quantum states a Hubble volume can be in is approximately 2 raised to the power of 10 to the power of 118. That's 2T-118, or if you prefer, about 118, 10 raised to the 10 to the 118th, a double exponential number, a power tower, a number so tall that the exponent itself has 118 digits. Every possible arrangement of every particle, every quantum field, every configuration of matter and energy that could fit inside your bubble, that's the total. That's the deck. And that deck is finite. So the Pigeonhole engine has its fuel. Infinite boxes, finite deck, guaranteed repetition. Now, who put all of this together into a single, unified argument about what it means for you, sitting wherever you are in the dark? Who looked at the pigeonhole principle and the Bekenstein bound and the flat geometry of the universe and said, put these things together and here is what follows? That was Max Tegmark. Tegmark is a cosmologist at the Massachusetts Institute of Technology, Swedish-born, and by most accounts one of the more adventurous thinkers in contemporary physics. Adventurous in the sense of being willing to follow an argument wherever it goes, even when it goes somewhere that makes people deeply uncomfortable. In May of 2003, he published a piece in Scientific American under the title Parallel Universes, and it landed with a particular kind of quiet force. It wasn't flashy, it was careful. It laid out an argument in steps, each step defensible, and then invited the reader to sit with what the steps implied. The piece introduced what Tegmark called the Level 1 multiverse. It's worth understanding what he meant by levels, because the taxonomy matters, and because the internet has done considerable damage to the distinctions. Tegmark organized the different kinds of parallel universes that serious physics points to into 4 levels, ranging from the most conservative and physically modest to the most radical and philosophically vertiginous. He later expanded this into a book, Our Mathematical Universe, published in 2014. But the 4-level framework was already fully formed in that 2003 article. Level 4 is the deepest and strangest, the idea that all mathematical structures exist as physical reality, that the universe is, at bottom, mathematics all the way down. Level 3 is the many worlds interpretation of quantum mechanics. The idea that every quantum event that could go multiple ways actually does go multiple ways, in branching parallel versions of reality, one for each possible outcome. Level 2 involves other bubble universes produced by eternal inflation, possibly operating under different physical laws and different constants of nature. And Level 1, the first level, the ground floor, the most conservative of the 4, is simply this. Regions of space beyond our observable horizon, operating under the same physical laws as we have here, that we cannot see because light hasn't had time to reach us. No new physics, no quantum branching, no alternative laws of nature, just space going on with the same rules everywhere. And the pigeonhole principle doing its work. Brian Greene, the physicist and author who catalogued all the major multiverse ideas in his 2011 book, The Hidden Reality, puts it plainly. Level 1 is the least controversial multiverse precisely because it demands so little. You don't have to believe in quantum splits, you don't have to believe in extra dimensions or bubble universes with exotic physics. You only have to believe one thing, that space keeps going, that the universe doesn't have an edge, a wall, a place where the fabric simply stops. That the 46.5 billion light-year bubble we can see is not all there is, but just our portion, just the slice we can access, surrounded by more of the same stretching outward without end. If you believe that, even tentatively, the rest follows with the inevitability of long division. And that's what makes the level 1 argument so philosophically interesting and so philosophically treacherous at the same time. Because on one hand, it requires almost nothing exotic, no new science, no speculation about unknown forces. On the other hand, it leads to a conclusion that sounds extravagant beyond imagining, that there is right now a precise physical duplicate of you reading this sentence in a body identical to yours, inside a world identical in every observable detail to the one you inhabit. And the only thing standing between that sounding like obvious science and sounding like science fiction is whether space is actually infinite, which we will come to. We'll come to the uncertainty and we'll sit with it. And we'll be honest about what we know and what we don't. But for now, let's stay with the machinery, because there are two hidden assumptions built into the level Y argument that most treatments skim past, and they matter more than they're usually given credit for. The first is called the cosmological principle. This is one of the foundational assumptions of modern cosmology, and it has an elegant, almost democratic quality to it. The cosmological principle says that on the largest scales, the universe looks the same from everywhere. Not exactly the same. If you zoom in, you see galaxies here and empty voids there, the great webbing of filaments and walls and supervoids that make up the large-scale structure. But zoom out far enough, pull back to scales above about 300 million light-years, and the universe becomes statistically uniform, homogeneous, the same composition and density everywhere. Isotropic, the same in every direction you look. The same game played by the same rules, dealt from the same deck, wherever you sit at the table. If the cosmological principle holds, then the regions beyond our horizon are drawing from the same possibilities we are. The deck doesn't change out there. The laws of physics don't bend or shift or become something alien past the boundary we can see. Every distant Hubble volume is working with the same materials, the same forces, the same quantum rules. It is, in the deepest sense, the same universe all the way out. Now, the cosmological principle is empirically supported. We've tested it. Large-scale surveys of galaxies, enormous projects like the Sloan Digital Sky Survey, have mapped the universe's structure across billions of light-years and confirmed, to good approximation, that the universe is indeed uniform above those large scales. The cosmic microwave background, the faint afterglow of the early universe, is essentially the same temperature in every direction we look, with only tiny fluctuations, 1 part in 100,000, rippling across it. This is some of the most beautiful evidence we have for the cosmological principle. The whole sky, the whole early universe as we can observe it, is nearly perfectly smooth. But empirically supported is not the same as proven everywhere. Our tests extend only as far as we can see. The cosmological principle is an extrapolation, a reasonable one, a scientifically motivated one, but still an extrapolation beyond the horizon. We're assuming the deck stays the same in rooms we've never entered, because every room we have entered has been the same. It's a good assumption. It might be a perfect assumption, but it is an assumption, and the level Y argument needs it. If, just hypothetically, something changes out past our horizon, if the laws of physics or the statistical properties of matter are somehow different out there, then the same deck everywhere foundation weakens, and the argument for exact copies gets shakier. We have no reason to believe this happens, but we have no way to check. The horizon is the horizon. The second hidden assumption is subtler and a little harder to state cleanly, but it's important. The pigeonhole argument says that every arrangement in the deck will eventually appear, given enough Hubble volumes to draw from. But that's only guaranteed if the drawing is, in some meaningful sense, random. If the initial conditions of matter and energy across space varied enough to actually explore the full range of possibilities, rather than all landing on the same narrow cluster of configurations. Think of it this way. Suppose you have a deck of cards with 1 billion different cards, and you draw from it infinitely many times. If the draws are random and independent, every card appears infinitely often. But if the drawing process itself is biased, if some deep structural reason makes certain cards wildly more likely and others essentially impossible, then you might draw infinitely many times and still never get certain configurations. The repetition argument depends on the drawing being genuinely random, or at least random enough to sweep across the possibilities. For the another you conclusion, this means the early universe's initial conditions need to have varied enough across different regions of infinite space to have actually produced every physically permissible configuration of matter, rather than just the configurations that some deep structural principle makes overwhelmingly probable. We believe this is the case. The fluctuations in the early universe that seeded all of today's structure do appear to be consistent with random quantum noise, which would naturally explore the space of possibilities. But this too is an extrapolation, an assumption we fold in quietly when we say the argument holds. George Ellis, and we'll spend more time with Ellis later because his skepticism is the most rigorous and worth taking seriously, noted that multiverse arguments, including level 1, tend to require assumptions about regions we can't observe and processes we can't fully verify. It's not that he thinks they're wrong, it's that he wants us to see clearly which parts of the argument are physics and which parts are plausible extrapolation wearing physics clothing. That distinction matters more than it might seem, and we'll return to it. But for now, with the machinery laid out, the Bekenstein bound giving us finitely many states, the cosmological principle giving us a uniform deck, Tegmark's level 1 framework giving us the combinatorial scaffolding. The argument stands, and it's remarkably clean. There are no exotic ingredients. There's no hand-waving about dimensions we can't detect or forces we've never measured. It's pigeons and pigeonholes dressed in the most serious physics available, pointing toward the most extraordinary conclusion imaginable. Infinitely many regions of space, each drawn from a finite set of possible states, each operating under the same laws. Every state appears, including yours. And let's be careful here about what every state appears actually means in the specific case of you. This isn't a vague or approximate claim. In Tegmark's own words, in that 2003 Scientific American article, and in the subsequent work, the duplicate is exact, not similar, not a version of you who made different choices and is now living a recognizable but divergent life. Exact. Every atom in your body, every neuron in your brain, the precise electrochemical state of your nervous system at this instant, the specific arrangement of proteins in your cells, the exact distribution of every molecule in the air around you, the precise configuration of every object in your room, all of it replicated perfectly in a Hubble volume sitting at a particular distance in the dark. The copy is reading this sentence, not a sentence like it, this one. The copy has the same memories as you, feels the same sleepiness, or the same gentle floating that comes between sleep and waking, has the same small ache somewhere, if you have one, the same fragment of a melody that's been stuck in their head. Because all of those things are physical states of a physical system, and the copy is an exact physical duplicate. Now, the obvious question, the one that pulls you toward wakefulness, a little even through the comfortable darkness. How far away? Tegmark calculated this. The calculation is necessarily approximate. The precise exponent shifts depending on the physical assumptions you fold in, and Tegmark says so in the appendix of his paper, carefully flagging which choices produce which numbers. But the qualitative answer is robust. It's a double exponential number, a power tower, and the bottom level of the tower is astronomical. For the nearest Hubble volume that is an exact duplicate of your own, a full copy of the entire observable universe around you, not just the you inside it, the distance is approximately 10 to the power of 10 to the power of 118 meters. That's 10, 10, 118 meters. The exponent has 118 digits. To write out that distance in ordinary decimal form, you would need to write the digit 1 followed by a number of zeros so vast that the number of zeros itself cannot be written without using exponential notation. You could not fit the number of zeros on all the paper in the observable universe. And for the nearest exact copy of just you, just the local configuration of matter that is your body, not the whole surrounding bubble, the distance is 10 to the power of 10 to the power of 28 meters. 10 is 1028. Still a double exponential, still a power tower. The exponent now only has 28 digits, which sounds smaller, and in some sense is, but even this smaller number is so incomprehensibly large that all our usual measuring rods dissolve against it. We'll spend more time with these numbers and with what it takes to really feel them in the next part of our journey. But before we leave the machinery and its assumptions, there's one more thing to mention. One more ingredient in the case for taking all of this seriously aside, and it comes from a completely different direction. It comes from what happens at the very beginning of the universe: eternal inflation. The name sounds grand and slightly ominous, and it is, in its own way, both of those things. The theory was developed by Alan Guth, the cosmologist who originally proposed the concept of cosmic inflation in the early 1980s, and then extended and deepened by Andrei Linde and Alexander Vilenkin, among others. The idea of inflation, that the very early universe went through a period of extraordinarily rapid exponential expansion, smoothing out and flattening space and planting the seeds of all the structure we see today, is well supported and is now part of mainstream cosmological thinking. But Guth and Linde noticed something about their own theory. Once inflation begins, it doesn't want to stop, at least not everywhere at once. The quantum fluctuations that drive inflation are random, and in most regions of space they keep the inflationary process going, while in some rare pockets the process ends and a bubble of ordinary, non-inflating space appears. Our universe, our entire observable universe, might be one of those bubbles, a region where inflation happened to end, leaving behind the relatively calm, structure-filled cosmos we inhabit. But in this picture, inflation never stops globally. It keeps going eternally in the vast majority of space, continually spawning new bubble universes, each one a new patch of non-inflating space, each one potentially the size of an observable universe or larger, each one a fresh start. Eternal inflation, if it's correct, produces space in quantities that make even large feel like a timid word. It produces infinite space, not by fiat, not by assumption, but as a natural consequence of the dynamics of the inflationary field. And if eternal inflation produces infinite space, it gives the level 1 pigeonhole argument exactly what it needs. Andrei Linde and his colleague Vitaly Vanchurin tried to put an actual number on how many distinguishable universes eternal inflation could generate. The attempt was published in Physical Review D in 2010. Their answer, depending on the assumptions they used, was something like 10 to the power of 10 to the power of 7. 10 plus 10, 7. Which sounds at first like a somewhat less enormous number than Tegmark's estimates. And it is in the sense that 10 to the 10 to the 7 is smaller than 10 to the 10 to the 118. But let's be clear about what 10 to the 10 to the 7 actually means. 10 to the 7th power is 10 million. 10 to the power of 10 million is a number with 10 million zeros. 10 to that power has a number of zeros that itself has 10 million digits. We are, in the most literal sense, beyond the reach of intuition before we even finish reading the number aloud. What Linde and Van Turin were counting wasn't exact copies of us, in the sense Tegmark meant. They were counting something more like the number of meaningfully distinct cosmological histories that eternal inflation could generate. But the point is the same. The machinery produces staggering variety, staggering quantity, and space on scales that beggar everything we mean by the word vast. None of this proves the level Y copies are real. The eternal inflation picture is a leading framework taken seriously by many working cosmologists, but it is not confirmed. The signatures of inflation are consistent with what we observe: the flatness of space, the spectrum of fluctuations in the cosmic microwave background. But eternal inflation specifically, the runaway global version that never stops, is harder to test and remains firmly in the realm of compelling but unconfirmed. We don't have a bubble detector, we can't look next door, but here is what we have: two independent lines of reasoning: the level Y argument from flat, infinite space, and the eternal inflation argument from the dynamics of the very early universe, both pointing in the same direction. Both suggesting that if the universe is as large as the best theories and the most straightforward reading of the data allow, then we are not alone in the deepest possible sense. Not in the sense of other life somewhere in the cosmos. In the sense of exact copies, physical duplicates, the same you repeated infinitely, spread across a space so vast that our entire observable universe is to it nothing. A speck, a grain, a vanishingly small fraction of a fraction of a fraction of what exists. The machinery is in place. The pigeons are counted, the pigeonholes are finite. Now let's make the numbers felt. So, how many holes are there? This is where the physics becomes very precise and very strange, and the two things feed each other in a way that is almost beautiful once you sit with it long enough. You don't have to hold every detail, just let it drift over you. The question of how many distinct states a region of space can be in, how many different arrangements of matter and energy are possible inside one Hubble volume, sounds like it might have an infinite answer. If space is a continuum with infinitely fine gradations of position and momentum, then surely the number of possible configurations is itself infinite. And if the number of possible arrangements is infinite, the pigeonhole principle fails immediately. Infinitely many rooms, infinitely many arrangements, no repetition guaranteed. But here's where it gets strange, and this is the part most versions of this story quietly skip over, because the physics underneath it is genuinely deep. The universe is not infinitely fine-grained, it is granular, informationally granular. And the reason we know this comes from one of the more remarkable convergences in modern theoretical physics, a set of ideas that grew out of thinking very carefully about black holes. In 1981, a physicist named Jacob Bekenstein, working on questions about what happens to information when matter falls into a black hole, worked out something surprising. He showed that the maximum amount of information that can be stored inside any region of space is not proportional to its volume, the way you might expect, but to its surface area. The boundary, not the interior. A sphere's worth of information fits on the skin of the sphere, not in the meat of it. This is the Bekenstein bound, and at first it seems like a curiosity, a technical result from the exotic physics of black holes. But then Gerard 't Hooft and Leonard Susskind took it further. What if this wasn't a special property of black holes? What if it was a fundamental feature of space itself? What if reality is, at the deepest level, a kind of hologram, where the information describing a volume is encoded on its surface? This is the holographic principle, and it carries a consequence that lands directly in our story. If the maximum information content of any region is finite, capped by its surface area, by a hard physical limit rooted in the thermodynamics of black holes, then the number of distinct quantum states available to a Hubble volume is finite. Not just practically finite, not just too large to count, mathematically, provably, fundamentally finite. And Tegmark, working from this, put a number on it. The total number of distinguishable quantum states available to a region the size of our observable universe is roughly 10 to the power of 10 to the power of 118. Written the way mathematicians write it, 10 raised to the exponent 10 raised to the exponent 118. Let that sit for a moment. 10 to the 80 is the number of atoms in the observable universe. Everything you have ever seen or imagined seeing, every star, every planet, every grain of interstellar dust. That number has 80 digits. 80? A googol is 10 to the 100. 100 digits. It is famously larger than the number of atoms, larger than the number of any particle in the visible universe. A googolplex is 10 to the googol, 10 raised to a number with 100 digits. Edward Kasner coined the term in 1940, and the standard illustration is that there is not enough room in the observable universe to write it out, even if every atom were a digit. The googolplex is so large it cannot physically exist as written text in our universe, and the number of possible states in a Hubble volume, 10 to the 10 to the 118, is larger, not a little larger, incomparably, category-shatteringly larger. The googolplex is to this number roughly what a single atom is to the observable universe, and even that comparison sells the gap short. But, and this is the thing, it is finite. That is the key, not big, finite. There is a ceiling. The number of possible arrangements of all the matter, energy, and fields inside a Hubble volume to any resolution that physics considers physically meaningful is a specific number. Enormous beyond imagination, but specific. Countable in principle, not infinite. Now the pigeonhole principle wakes up. The principle itself is almost embarrassingly simple, which is part of what makes it so powerful. If you have more pigeons than pigeonholes, at least one pigeonhole must contain more than one pigeon. If you have infinitely many pigeons and finitely many pigeonholes, then every pigeonhole contains infinitely many pigeons. Not probably, not on average, necessarily. Substitute infinitely many Hubble volumes for pigeons. 10 to the 10 to the 118 possible quantum states for pigeonholes. Under the assumption that space is infinite, and that the matter within it is statistically uniform, drawn from the same physical laws and the same statistical deck everywhere, then every possible state must appear infinitely many times. The duplication is not a statistical likelihood, it is a combinatorial certainty. It is, under those assumptions, as close to a theorem as cosmology gets. This is what Max Tegmark called the Level 1 multiverse, and he was careful, and it is worth being careful here too, to point out what makes it remarkable. It requires no new physics. None. Not a single equation that isn't already standard. No exotic dimensions, no quantum branching, no colliding brains, no speculative extensions to the standard model. Brian Greene, cataloguing the full multiverse taxonomy in his 2011 book, The Hidden Reality, makes the same point. Level 1 is the least controversial multiverse on offer. It asks only one thing of you, one concession, one premise. That space goes on forever. If you grant that, the copies follow the way morning follows night, not poetically, logically. And Tegmark calculated the distances. He published the analysis in Scientific American in May 2003 in a paper called Parallel Universes, and he worked it through more carefully in his 2014 book, Our Mathematical Universe. The nearest Hubble volume in a state identical to ours, a patch of space the same size as everything we can see, containing the same galaxies in the same arrangement, the same planets in the same orbits, the same you, is on average about 10 to the 10 to the 118 meters away. The nearest region containing a copy of you, specifically, not the whole observable universe, just your Hubble volume neighborhood, your galaxy, your star, your planet, your room, you, is closer. Still incomprehensibly far, but closer. about 10 to the 10 to the 28 meters. And here is the thing about that number that Tegmark himself points out, and that almost nobody who repeats the number bothers to explain. Whether you measure the distance in meters or in light years or in Planck lengths, the smallest physically meaningful distance, roughly 10 to the negative 35 meters, the answer does not change in any meaningful way. Switching from meters to Planck lengths adds about 35 to the exponent at the bottom of the tower. 10 to the 28 becomes something like 10 to the 63, but 10 to the 10 to the 28 and 10 to the 10 to the 63 are, for all practical and mathematical purposes, the same order of incomprehensibility. The bottom exponent changes, the character of the number does not. The units dissolve. This is a property unique to double exponential numbers. At this scale, your choice of ruler is genuinely provably irrelevant. You are not picking a measuring system. You are picking which digit changes at the far end of an exponent that already has 28 digits. It does not matter now. These two assumptions, that space is infinite and that matter is statistically uniform everywhere, are not trivial. They need to be named. The second one has a name in cosmology, the cosmological principle. It holds that on the very largest scales, above roughly 300 million light-years, the universe looks the same in every direction and from every location. Homogeneous and isotropic. No special places, no special directions, the same statistical deck dealt everywhere. Below those scales, the universe is famously lumpy. Galaxies, voids, filaments, the vast cobweb structure of the cosmic web, superclusters like Laniakea, stretching hundreds of millions of light-years across. The cosmological principle is not a claim that every cubic light-year looks alike. It is a large-scale statistical statement. Zoom out far enough, and the universe smooths into something uniform. The evidence for it is solid, drawn from the large-scale structure surveys, from the smoothness of the cosmic microwave background. But it is a principle, an observed regularity, not a derived theorem. And it matters to the copy argument because it is what guarantees that distant Hubble volumes are drawn from the same physical deck as ours, that the pigeonholes are the same everywhere, not a different set of possibilities in some far region where the rules work differently. The first assumption in E infinity itself is the one the whole argument rests on and the one we have not proven. So let us stay with the number for a moment, because saying it aloud is one thing and actually feeling it is another. 10 to the power of 10 to the power of 28 meters. That is the distance on average to the nearest exact copy of you. You have heard large numbers before. You know the universe is big, but this number is doing something different from ordinary bigness, and it is worth sitting with that difference until it lands. Think about the atoms. Every atom in your body, every atom in your bed, every atom in the walls of the room where you are lying right now, added together with every atom in every planet, every star, every cloud of gas, every grain of dust across the entire span of the observable universe. The total comes to roughly 10 to the 80. That is a 1 followed by 80 zeros. A number you could not write out on a sheet of paper without squeezing your handwriting, but a number you could at least conceive of writing. 80 digits, manageable, finite in a way that feels almost cozy. Now compare it to the distance to your copy, expressed in meters. 10 to the 80. 10 to the power of 10 to the 28. The first number is a single exponent. The second is a double exponent, or an exponent of an exponent. And when you go from single to double exponential, you do not simply get a bigger number. You fall through a trapdoor into a different country of mathematics entirely. Here is what that means in practice. Imagine you could somehow line up all the atoms in the observable universe, all 10 to the 80 of them, and use each one to represent a zero in some number. You could write a number with 80 zeros that way, a 1 with 80 zeros trailing after it. Now imagine each of those atoms was not an atom but an entire observable universe, and each of those universes also contained 10 to the 80 atoms, and you used every single one of those atoms to write zeros. You would have 10 to the 160 zeros, a number that dwarfs the first so completely that the first one might as well not exist. And you would still not be close to the distance to your copy. Not even approximately close, not even close to close. This is why mathematicians developed a useful shorthand, a googol and a googolplex. A googol, the word coined by the American mathematician Edward Kasner in 1940, suggested charmingly by his 9-year-old nephew, is 10 to the 100, one followed by 100 zeros, bigger than the number of atoms in the observable universe by a factor of 10 to the 20th, a factor of 100 quintillion, and yet still just a number you could write out on a very long piece of paper. Not impossible, just large. A googolplex is 10 to the power of a googol, 10 to the 10 to the 100, and this is the famous one, the one people invoke when they want to gesture at something truly unwritable. A googolplex is so large that if you tried to write it out in standard notation, a one followed by a googol of zeros, you could not do it even if you used every atom in the observable universe as a single printed zero. The universe does not contain enough matter to hold the representation of the number. There is not enough room, not enough paper, not enough atoms. The googolplex is, in that very concrete sense, too large to write, and the distance to your nearest copy, in meters, is larger than a googolplex. 10 to the 10 to the 28 is smaller than 10 to the 10 to the 100, the googolplex, because 28 is less than 100. But we are also talking about the nearest copy of just you. The nearest copy of the entire observable universe, everything within 46.5 billion light-years of your position, sits at roughly 10 to the 10 to the 118 meters away. And that number is larger than a googolplex because 118 is greater than 100. So the nearest complete copy of all of this, your galaxy, your sun, your planet, your entire sky, is farther away than a number that is itself too large for the observable universe to contain. Sit with that and remember what we established earlier. You could measure this distance in light years instead of meters. You would subtract about 16 from the exponent at the bottom of the tower because there are roughly 10 to the 16th meters in a light year. Subtract 16 from 10 to the 28 and you get 10 to the 28 to all meaningful approximation. The exponent barely flickers. You could measure it in Planck lengths, the smallest meaningful unit of distance, which would add 35 to the bottom exponent. Still 10 to the 28, essentially unchanged. The units do not matter. The number is so top-heavy that rounding the bottom exponent by 16 in either direction is like rounding the height of a mountain by the diameter of a grain of sand. This is not the usual experience of numbers. In ordinary life, units matter enormously. 12 inches and 12 light-years are catastrophically different. But at double exponential scale, the unit of measurement becomes, in effect, irrelevant. You have slipped past the place where such distinctions exist. That is the number. That is where your copy lives. And now the natural question, why would the copy be exact? Not approximately you, not a cousin you, not a civilization that made similar choices you. Why exactly you? Every atom, every neural connection, every memory, every half-formed thought you are carrying right now into sleep. The answer goes back to what the pigeonhole principle is actually counting. Tegmark's argument does not deal in rough approximations. It deals in quantum states. The complete physical description of a region of space, every particle, every field value, every quantum number, every entanglement, constitutes a single quantum state of that region. Two regions in the same quantum state are, in the most precise physical sense, identical, not similar, identical. There is no further fact that could distinguish them. So when we say a distant Hubble volume is an exact copy, we mean it is in the same quantum state as ours, and that means the you over there, the version of you on the other side of that inconceivable distance, is not merely someone who looks like you, someone who chose the same career and fell in love with the same people. That version of you has the same arrangement of every atom in their brain as the arrangement in yours, the same synaptic weights, the same half-second of wondering whether they will actually fall asleep tonight, encoded in exactly the chemistry that encodes it in you. The same memories of the same things that feel significant. The same small embarrassment from 3 years ago that still occasionally resurfaces for no reason. Because consciousness, as far as science can determine, arises from physical arrangement, and physical arrangement in that distant Hubble volume is identical. This is the part Tegmark is explicit about. He is not talking about a philosophical near twin. He is talking about an exact physical duplicate, identical at the level of quantum state, which means identical at every level above that: atomic, molecular, cellular, neural, experiential. That version of you is reading or listening to these exact words at this moment, or rather, at some moment that corresponds to this one from the frame of their local reference, though we will come back to the messiness of at this moment across cosmic distances in a little while. The thought is strange enough to make you want to sit up. But do not. Stay comfortable. There is more. Because here is the thing that most retellings of this idea skip past, and it is, in some ways, the more haunting version of the story. The exact copy, the one at 10 to the 10 to the 28 meters, is genuinely exact, identical in every atom. But it is also the rarest kind of copy. The most common copies are the near copies, the versions of you that differ from you by one atom. Think about what that means. Somewhere, much closer than the perfect duplicate, is a version of you whose body is identical to yours, except that a single hydrogen atom at the edge of your left thumbnail is in a slightly different quantum state. That's it. One atom. Everything else, every memory, every thought, every physical process is the same. The difference would be undetectable by any conceivable test. That version of you is, for all practical purposes, you. And there are vastly more such copies than there are perfect ones. Combinatorially, the number of ways to differ from you by exactly one atomic change is roughly equal to the number of atoms in your body, tens of trillions, multiplied by the number of possible alternative states for each. The number of ways to be a near you is orders of magnitude larger than the number of ways to be exactly you, which means near copies are proportionally far more common and therefore far closer. And then there are the copies that differ by 2 atoms. More numerous still and closer still in a statistical sense. You see the pattern. The farther you relax the definition of copy, the denser the crowd becomes, and the shorter the distance to the nearest member of that crowd. So the landscape your copy self inhabits in this infinite space is not a rare phenomenon. It is a crowd. Most of that crowd differs from you in ways that are physically trivial, but experientially might be significant. One neuron that fired slightly differently. One memory that encodes slightly differently. One moment that branched in a way too small to feel but real enough to slowly propagate over decades into a different life. And the rarest, most precious version in that crowd, the one who is atom for atom, quantum state for quantum state, identical to you, sits at the back of the crowd, farthest away, separated from you by the number we have been sitting with all night. This is the richer picture, not one copy, a gradient, a vast and infinitely populated gradient of near use, exact use, and everything between, stretching outward through space that, if the premise holds, never ends. Now, there is a misreading of this idea that floats around, and it is worth clearing up before it settles in, because it is both common and wrong. And it matters because getting it wrong changes what the argument is actually saying. The misreading goes like this. If the universe is infinite, then everything possible must happen somewhere. A version of you who can fly, a version of you made of cheese, a version of you who discovered a consistent way to travel faster than light. A universe where mathematics gives different answers. This is not what the argument says, and it is not technically permitted by it. The copies, the exact ones, the near ones, the whole infinite gradient, are copies that obey the same laws of physics as you do. The same four fundamental forces. The same constants of nature. The same rules governing what arrangements of matter are stable, what processes are possible, what structures can exist. The deck that gets reshuffled across infinite space is a deck drawn from the set of all states consistent with those laws. It is a large deck, and we 10 to the 10 to the 118 possibilities for a Hubble volume, recall, but it is not an unlimited deck. A version of you who can fly unaided does not exist in the Level 1 multiverse, because human flight unaided by any physical mechanism is not a permitted state under the physics we have. A universe where 2 plus 2 equals 5 does not appear, because mathematical truth is not a physical arrangement that can vary across space. A copy of your brain with a memory it could not have acquired through any physical process is not in the deck. What the argument gives you is every physically realizable state, repeated infinitely often. That is already more than enough to be astonishing. You do not need to add impossible things to make it wonderful. The possible things under these laws across this range are already staggering. This distinction matters for another reason too. Sometimes this idea gets tangled up with a completely different proposal, the many worlds interpretation of quantum mechanics, which sits at Tegmark's level 3 in the taxonomy of multiverses, and which involves an entirely separate mechanism. In the many worlds picture, first proposed by Hugh Everett in 1957, every quantum measurement, every quantum event that could go one way or another, actually goes both ways. Both outcomes happen, but in branches of the universal wave function that no longer interact with each other. Every moment, at every quantum decision point, the universe is branching into a vast and growing tree of versions, each internally consistent. The you who read this far is in one branch. Another version of you fell asleep on the second paragraph, in another branch that diverged from yours at that quantum moment. This is fascinating, and it is a genuinely serious proposal in the foundations of physics, but it is not what we have been talking about tonight. The level 1 picture, the copies across infinite space, requires no quantum branching. It requires no new physics at all. It does not require any alteration to the equations governing reality. It requires only that you take the spatial extent of the universe as described by standard cosmology and let it be truly, literally, infinite in extent. That is all. No branching, no wave functions splitting. Just space, going on and on and on, containing matter distributed according to the same statistical rules everywhere until the finite number of possible configurations must recur. Level 1 is, in Tegmark's own framing, the least controversial of the multiverses, the one that demands the least from you, the one where the extra ingredient, infinity, is not some exotic new physics, but simply the default behavior of a flat universe continued to its logical conclusion. And that is actually part of what makes the whole situation so strange. The another you conclusion, which sounds like it belongs in the most extravagant science fiction, actually requires less speculative machinery than any of the other multiverse proposals. It is not the wildest claim in the family, it is the tamest. The ones above it in the taxonomy will be at level 2, level 3, level 4. Each require progressively more exotic foundations. Level 1 needs only one thing. That space is infinite, which brings us to an independent reason why many cosmologists take infinite space seriously, even though they cannot prove it from direct observation. That reason is eternal inflation. The story begins with inflation itself, the period of extraordinarily rapid, exponential expansion that cosmologists believe took place in the very earliest moments of the universe, within the first tiny fraction of the first second after the Big Bang. Inflation was proposed by Alan Guth in 1980, and it solves a cluster of otherwise puzzling features of the universe. Why it is so flat, why it is so smooth and uniform in all directions, why it does not appear to contain certain exotic relics that earlier theories predicted. Inflation does this by taking whatever initial conditions existed and stretching them dramatically and uniformly, ironing out irregularities the way you smooth a bedsheet by stretching it. What remains is a very flat, very uniform universe, which is what we observe. But here is what Guth, Andrei Linde, and Alexander Vilenkin realized when they looked more carefully at the dynamics of inflation. There is a very natural version of inflation that once started, never fully stops. The inflationary process is driven by a quantum field in an unstable high-energy state. As it decays, it releases energy and drives the rapid expansion. But quantum mechanics means that this decay is not uniform. It happens in different places at different rates, with random quantum fluctuations determining the local pace. In some regions, inflation ends and a universe like ours emerges. Matter condenses, galaxies form, stars light up. But in other regions, inflation continues, and because the expansion during inflation is exponential, the regions that are still inflating are generating new space faster than they are converting it into settled universes. The total volume in the inflationary state keeps growing even as bubbles of settled physics keep forming within it, like islands of calm appearing in a sea that keeps expanding faster than the islands can spread. In this picture, inflation is eternal in the forward direction. It never globally stops. New bubbles, new regions of settled physics, keep forming, and each one is effectively a vast universe of its own. Our entire observable universe, everything within the 46.5 billion light-year sphere we discussed at the start of our evening, is one such bubble. And the total volume across all of these forever inflating regions and the bubbles they generate is not just large. It is in this model unbounded, infinite. Eternal inflation is not proven. It is a theoretical framework, a natural extension of inflation, not yet confirmed by direct observation. But it is a widely studied proposal within mainstream cosmology, and it provides an independent reason to take seriously the idea that the universe is genuinely infinite in extent, not just big, but truly, literally, without end. And if the universe is infinite in extent, then the level 1 argument applies. The copies follow. Andrei Linde and his collaborator Vitaly Vanchura, in a paper published in Physical Review D in 2010, tried to do something remarkable: to count the number of distinguishable universes that the inflationary process could produce. Not all possible universes, just the ones that inflation, according to its own dynamics, is plausibly capable of generating. Their answer, and this is a real number from a real published paper, was on the order of 10 to the 10 to the 7th, or larger, depending on assumptions, 10 to the 10 million. A double exponential number, already familiar territory for us tonight, but smaller than the state space of a single Hubble volume. The universe, even in this model, appears to generate an extraordinary variety of configurations, but a finite variety, which over infinite space still repeats infinitely often. The Linde and Van Turing count is an attempt to do honest bookkeeping in a framework that is inherently difficult to constrain. It acknowledges what the argument requires and tries to put real numbers to it. The numbers are extraordinary. The qualitative conclusion, infinite copies, infinite repetition, does not depend on whether the exact exponent is 7 or 70. It depends on whether the space is truly infinite. That is always the load-bearing word. So here is where we stand, in the gentle dark, part-way through the night. We have the number, 10 to the 10 to the 28 meters, for the nearest exact copy of you. 10 to the 10 to the 118 meters, for the nearest copy of everything you can see. Numbers that dwarf the number of atoms in the universe, that dwarf a Googleplex, that sit in a region of mathematics where the unit of measurement ceases to matter. We have the logic that generates that number, the pigeonhole principle operating on a Hubble volume's worth of possible states, a finite number bounded by the Bekenstein bound, the holographic principle over an infinite space where matter is distributed statistically the same way everywhere. We have the texture of what the copy means, exact, down to quantum state, down to every atom in your brain, down to this thought, and the richer crowd of near copies differing by 1 atom, 2 atoms, gradually many, closer and more numerous, the less precise the match. We have the clarifications. The copies obey the same physics, so no flying you. The mechanism is spatial, not quantum branching, so this is not the many worlds interpretation of level 3. The whole argument needs no new physics, making it the most conservative of the multiverse proposals. And we have a second, independent path to the same destination. Eternal inflation, in the work of Guth, Linde, and Vilenkin, which provides a dynamical reason to expect infinite space and infinite repetition as a consequence of how the very earliest moments of the universe unfolded. What we have not yet done, and what the night still holds, is turn this same rigor back on its own foundation. Because everything we have said, every step of that logical chain, every astonishing consequence, the exact copy, the near copies, the unreachability, the guarantee that is also a certainty, all of it begins with a single word, if. If space is truly infinite. And that word is where we are going next. Not to soften the wonder, but because the most honest thing the argument earns, the thing that makes it genuinely profound rather than merely spectacular, is the fact that the most consequential possible claim about reality might be the one we can never confirm. That is the seesaw this night balances on. The conclusion is nearly airtight given the premise, and the premise is something we cannot yet prove and may never be able to. Before we get there, let the number settle a little longer. You are lying somewhere in space, in a Hubble volume, a sphere about 46.5 billion light-years in radius, filled with hundreds of billions of galaxies, each containing hundreds of billions of stars, each potentially orbited by worlds. And on one of those worlds you are here, awake or nearly asleep, listening. And somewhere, at a distance, that makes the entire observable universe look like a single atom by comparison, makes the Googleplex look like a single atom by comparison, there is someone in an identical arrangement. Same room, same bed, same sky outside, same stars in the same positions, same quiet, listening to the same words, carrying the same tiredness into the same dark. And the closest one of them, the nearest to exact, differs from you by a single atom somewhere in the edge of a thumbnail and is much, much closer, though still far beyond anything we could ever reach. There is a whole crowd out there, a gradient of you, from almost you to exactly you, filling the infinite dark in every direction. That is what the math says if the universe goes on forever. And whether it does, that is still open. That is where we go next. Let us stay with the numbers a little longer because they deserve it. You have heard the phrase the number of atoms in the observable universe before, probably as a shorthand for enormity. 10 to the power of 80. That is a 1 followed by 80 zeros. Written out on paper in a reasonable font, it would stretch a few meters. It fits on a single line. 80 zeros is large the way a mountain is large, impressively, visibly, concretely large. You can gesture at a mountain. You can photograph it. You can hold the idea of it steadily in your mind. Now, the distance to your nearest exact copy is 10 to the power of 10 to the power of 28 meters. Read that again slowly. 10 to the power of 10 to the power of 28. The exponent is not 28. The exponent is 10 to the 28, which means the exponent itself has 29 digits. You are not raising 10 to a large number. You are raising 10 to a number so large it cannot be written without its own exponential notation. This is what mathematicians call a double exponential, a power tower, and the difference between a single exponential and a double one is not a matter of degree, it is a matter of kind. Think of it this way, 10 to the 80, all the atoms in everything we can see, is a single exponential, a big number but a flat one in the sense that you can at least state the exponent in plain language. 80, say it, it takes less than a second. The distance to your nearest copy requires an exponent you could not say because saying it would require saying a number with 29 digits, which would take roughly a minute, and that number would describe only the exponent, not the distance itself. Edward Kasner introduced the googol in 1940 as a name for 10 to the power of 100. A googol. His young nephew reportedly coined the word, which is a lovely detail. A googol has 100 zeros. Written out, it takes a few lines on a page. And then Kasner defined the googolplex as 10 to the power of a googol. 10 to the 10 to the 100. The googolplex became famous, in a gentle way, as an example of a number so large it cannot be written out in full, even if you use every atom in the observable universe as ink and every particle of space as paper. The observable universe simply does not contain enough room for all those zeros. The distance to your nearest copy, in meters, is larger than a googolplex. Not larger in the way that, say, a billion is larger than a million. Larger in the way that the googolplex is larger than the number 80. A different tier entirely. The googolplex sits at 10 to the 10 to the 100. Your copy is at 10 to the 10 to the 118. Those extra 18 powers in the exponent, the difference between 10 to the 110 to the 118, represent a multiplicative leap so vast that the googolplex, that famous illustration of incomprehensibility, becomes by comparison something almost quaint. And here is the detail that stops people cold when they first really hear it. That distance, 10 to the 10 to the 28 meters, does not change meaningfully if you switch your units. If you measure it in light years instead of meters, you adjust the bottom of the tower by a small constant, because a light year is just a number of meters, and dividing by that number subtracts a modest amount from the exponent at the base. But the base of the tower is already 10 to the 28. Subtracting a few dozen from 10 to the 28 is like removing a single grain of sand from a beach and calling it a shorter beach. The distance, for all practical and impractical purposes, is the same whether you state it in meters, light years, Planck lengths, or any other unit a human being has ever conceived. The choice of ruler is genuinely irrelevant. This is not a rhetorical flourish. It is a direct mathematical consequence of what a double exponential actually is. So that is the nearest exact copy of you. The nearest perfect duplicate of your entire Hubble volume, every galaxy, every star, every mote of dust, every atom in your body in its precise arrangement, the whole sphere 46.5 billion light-years across, reproduced in its entirety, sits at roughly 10 to the 10 to the 118 meters, a number that makes the Googleplex look the way a single atom looks next to the observable universe. Now, what exactly does exact mean here? And why does it have to be that precise? In the level wine picture, what makes you you is not something vague or spiritual, though you are welcome to believe in that separately, and this does not touch it. What the physics means by you is the precise arrangement of every atom in your body and brain within your Hubble volume, the position of every particle, the state of every neuron, the specific pattern of connections that encodes every memory, every habit, every preference, every fear, every word you know, every face you love. All of it is physical, and all of it is, in principle, a particular arrangement of matter in space. A true duplicate volume, by definition, reproduces that arrangement exactly. Max Tegmark was quite explicit about this. The copy is not reading a similar sentence, the copy is reading this sentence, in the same font, in the same room, in the same state of wakefulness or near sleep, having had the same thoughts in the same order leading up to this moment. If you are a little cold right now, the copy is a little cold. If there is a sound outside your window, the same sound is outside theirs. The duplication, under the combinatorial logic, is not approximate. It is exact down to every atom in every neuron. That is an extraordinary claim, and it deserves a moment. And yet, alongside that exact copy, much closer, statistically speaking, vastly more numerous, are the near copies. Versions of you that differ by a single atom somewhere in the edge of a fingernail. Versions that differ by one synapse in one corner of one memory. Versions where a single choice went the other way, not because of some mystical fork in a timeline, but simply because the initial conditions of that particular Hubble volume were arranged to produce that one different atom, that one different outcome. The near copies are not a curiosity appended to the main idea. They are, in a sense, the richer and stranger part of it, because the math of combinations works like this. The number of arrangements that differ from yours by exactly one thing is vastly larger than the number of arrangements that are exactly identical to yours, which is one by definition. And the number that differ by two things is larger still. The gradient runs from exactly you at astronomical distance up through a great flowering of almost yous, each one a little closer, each differing a little more. There is a version of you who is reading this with slightly different phrasing of the previous sentence still in mind. There is a version who put down whatever they were drinking a moment earlier. There is a version who made a different decision last Tuesday, and whose life from that Tuesday forward has been quietly, incrementally, recognizably different, and who is lying in a bed very much like yours, nearly asleep, in a universe indistinguishable from this one in almost every way. The closest of the near copies is much nearer than the perfect one. Still far beyond any horizon we could ever reach, still beyond anything we could observe or signal or verify, but nearer in the only sense the numbers allow. There is a whole crowd out there in the dark, a gradient of resemblance, a spectrum of almost you and nearly you and exactly you, filling the infinite space in every direction, if the universe goes on forever. Now, before you carry that image into sleep, there is one thing worth saying clearly, because it is something a lot of popular treatments of this idea quietly skip. The copies are real according to this logic, but they are not unlimited, they are not arbitrary. The universe, even an infinite one, does not conjure every imaginable thing. What the combinatorial argument guarantees is that every arrangement consistent with the laws of physics recurs. That word, consistent, is doing a great deal of work, and it matters. A version of you who can fly without wings does not appear, because that arrangement violates physics. A room that is a perfect square circle does not appear, because that is not a state physical matter can occupy. The infinite universe is not a warehouse of every conceivable fantasy. It is a warehouse of every possible physical configuration, and the laws of physics are the constraint that define what possible means. This is a correction of a very common misreading. The popular framing, there is a you who is a billionaire, a you who never made that mistake, a you who chose differently at every crossroads, is partially right and partially misleading. The you who chose differently exists only if that different choice was a physically available state of your brain and body and circumstances at that moment. Most of the time it is, because brains are physical things and small differences in initial conditions can produce large differences in behavior. But the point is that the guarantee is not a guarantee of imagination, it is a guarantee of physics. The copies are bounded by the same equations that bound you. This matters because it keeps the whole idea anchored. It is not magic, it is not a license for anything, it is a consequence of combinatorics operating within strict physical law across a canvas that, if it is truly infinite, is simply large enough for every lawful possibility to occur. And it is worth saying cleanly what this idea is not while we are here, because it is frequently and understandably confused with something else. The many worlds interpretation of quantum mechanics, what Max Tegmark called Level 3 in his taxonomy of multiverses, is a different beast entirely. In the many worlds picture, every quantum event that has more than one possible outcome causes reality to branch. Every measurement, every decay, every photon hitting a detector, the universe splits and both outcomes happen in separate branches. It is a proposal about what quantum mechanics actually means, about what happens when we are not looking, about the nature of the wave function. The Level 1 multiverse, your copy out there in the dark, is not that. It requires no quantum branching. It requires no new interpretation of physics. It requires no new physics at all. It requires only that space continues beyond the edge of what we can see, and that matter is, on large scales, spread with the same statistical properties everywhere. Given those two things, infinite space and a uniform distribution, the copies follow from combinatorics alone. From the same mathematics that tells you if you shuffle a deck of cards infinitely many times, every possible ordering must eventually appear. This is what makes the Level 1 multiverse the most conservative of all the multiverse proposals. Tegmark and Brian Greene both make this point. It is not a wild extrapolation. It is the straightforward consequence of taking seriously a universe that does not end. The quantum many worlds is a far more radical claim about the internal structure of reality. The Level 1 claim is almost boringly logical by comparison to Ake, given the premise. And the premise, of course, is the thing, the one unproven word on which all of this rests, which brings us to a separate and independent reason that serious cosmologists take that premise seriously, because the infinity of space is not only supported by the flatness measurements from the Planck satellite and WMAP, it has its own theoretical scaffolding built by some of the most careful thinkers in modern physics. Alan Guth first proposed cosmic inflation in 1980, the idea that in the first fraction of the first second after the Big Bang, the universe expanded at an extraordinary rate, smoothing out and flattening the space we see today. But Guth and others, particularly Andrei Linde and Alexander Vilenkin, went further. They developed what is called eternal inflation, the idea that inflation, once started, does not stop everywhere at once. Instead, it continues in some regions while others exit into the slower expansion we observe. Bubble universes form and grow and become regions like our own observable patch, while the space between them keeps inflating forever. The total volume in this picture is not finite and cooling, it is boundless and still generating. Eternal inflation is not confirmed. It is a theoretical framework, a well-developed one, supported by some observations and contested by serious critics. Paul Steinhardt, who helped develop inflationary theory, has turned sharply against it in recent years, arguing that eternal inflation makes so many predictions that it predicts nothing in particular, that it is unfalsifiable in a way that disqualifies it from being called science in the traditional sense. That debate is live and unresolved, but if eternal inflation is correct, it provides a physical mechanism for the infinite canvas the level 1 argument needs. It is not just that space might be infinite because we have not measured a curve in it. It is that there is a specific, detailed theoretical story about why space would be infinite. Because inflation never globally stops, and the volume it produces grows without bound. And Andrei Linde, together with Vitaly Van Churin, attempted something remarkable in a 2010 paper published in Physical Review D. They tried to count. Not to count the copies of you. That number, as we have seen, is beyond counting in any ordinary sense, but to count the number of distinguishable universes that eternal inflation might produce. The regions with different initial conditions, different arrangements of matter, different histories. They arrived at numbers around 10 to the power of 10 to the power of 7, and possibly larger, depending on the assumptions built into the calculation. 10 to the 10 to the 7, a double exponential again, smaller than the distance to your copy, but enormous in its own right. And a real, published attempt by real physicists to put a number on the variety that an eternally inflating cosmos would generate. It is the kind of number that makes you sit quietly for a moment. And so we arrive at the question the whole journey has been building toward. We have seen the engine, we have felt the numbers, we have understood why, if space goes on forever, your copy is not a poetic metaphor, but a near logical consequence, guaranteed, infinite in number, scattered across a canvas so vast that the distance to the nearest one dwarfs a googolplex, the way a googolplex dwarfs a single atom. The logic is clean. The math is firm. The pigeonhole principle doesn't negotiate. But now we turn the same rigor on the foundation itself. And when we do, we find something that is either reassuring or unsettling, depending on your temperament. The foundation has a crack. Not a fatal one. It hasn't collapsed under any physicist's weight yet, but it is there, running through the very first word of the argument, and once you see it, you cannot unsee it. That word is if. Let's go back to what we actually know, what our instruments have measured, what the data, as carefully as we can read it, actually says. The Planck satellite, a European Space Agency mission that spent years mapping the cosmic microwave background with extraordinary precision, gave us the most detailed portrait we have of the universe's geometry, and so did its predecessor, the WMAP satellite, the Wilkinson Microwave Anisotropy Probe, which began that mapping project in earnest in the early 2000s. Between them, these instruments measured something called the curvature of space. The parameter physicists write as omega sub k, or simply OK. Now think of curvature this way. If you draw a triangle on a flat piece of paper, its three angles add up to exactly 180 degrees. That is flat geometry, Euclidean. The geometry you learned in school. But if you draw a triangle on the surface of a sphere, a large one like the Earth, the angles add up to more than 180 degrees. The triangle bulges, space is positively curved, closed, finite, like the surface of a balloon. And if you imagine the opposite, a saddle shape that curves away from itself in every direction, the angles add up to less than 180 degrees. That is negative curvature, open, and it too has its own implications. A flat universe, OK equal to exactly 0, sits right at the boundary. And flatness is the key. Because a flat universe is compatible with being infinite. It can extend forever in every direction without curving back on itself. That is the geometry the level Y argument needs. And what did Planck find? It found that OK is approximately 0.01 with an uncertainty of about 0.02, which is to say, it found essentially zero. The universe, as far as we can measure, is flat, or very, very nearly flat. That sounds like confirmation. It sounds like the data is saying, yes, infinite. But here is where you need to be careful, because consistent with flat is not the same as proven flat. And even if the universe were proven to be exactly flat, a perfect Euclidean geometry extending in all directions, that still would not prove it is infinite. Flatness is a necessary condition for the simplest kind of infinite universe, but it is not sufficient. A flat universe can also be finite. Let that settle for a moment because it is counterintuitive. We tend to think of finite things as curved, like a sphere, closed, bounded. But mathematicians and physicists know of geometries that are flat and finite at the same time. They are spaces that have been, in a sense, folded or connected in ways that are not visible from inside. The most commonly discussed example is the 3 torus. Imagine the old arcade game Asteroids, if anyone in your household still remembers it. In that game, when your ship flies off the right edge of the screen, it reappears on the left. Fly off the top, you come back from the bottom. The screen is flat, not curved, but it is also finite. You can fit the whole playing field on a television. It wraps around. It has a topology that connects opposite edges. Space could be like that. 3-dimensional, flat by every local measurement and yet finite. Because if you traveled far enough in one direction, you would eventually loop back to where you started. A universe like that would still be locally flat. Triangles would still have angles adding to 180 degrees. OK would still read as 0, and yet it would be finite. No infinity, no guaranteed copies. In the early 2000s, a team of physicists, Neil Cornish, David Spergel, and Glenn Starkman, proposed a way to test this. They called it the circles in the sky method. The idea is elegant. If space has this kind of wraparound topology, then the cosmic microwave background that ancient light we use as our map of the early universe would contain matching circular patterns on opposite sides of the sky. You would see the same ring of temperature fluctuations in 2 different directions because those 2 directions are, in a topological sense, the same place. Like standing in a room where one wall is actually a mirror, or rather, where one wall is actually the opposite wall. The Planck team searched for those circles. They looked carefully with the best data available, and they found no convincing evidence of them. No matched rings, no signatures of a universe that wraps around. But, and this is the crucial word, that absence of evidence does not rule out a finite universe. It only places a lower bound on the size of any wraparound. If the universe does have a torus-like topology, the repeat distance must be larger than a certain minimum, larger than what the Planck survey could detect within the observable region. The data constrain the topology, but do not eliminate the possibility. The lower bounds from these searches suggest that if the universe is finite and toroidal, its characteristic size is at least around 250 times the diameter of the observable universe, possibly vastly more. And that is a good moment to breathe and remember what we said earlier in this journey. Finite does not mean small. A finite universe could be so enormous, so wildly beyond anything we can see or will ever see, that for all practical purposes, for all human purposes, it might as well be infinite. The distinction between finite but stupendously large and genuinely infinite may have no observable consequences whatsoever, even in principle, for any measurement we could ever make. So we have this situation. The data say the universe is flat or very nearly flat. That is consistent with infinite, but flat doesn't prove infinite. And there is an alternative. finite with unusual topology that fits the same data, though the search for its signature came up empty. And even if we could prove the universe is not toroidal, there are other finite topologies, other ways a flat universe could close in on itself that have different signatures and would require different searches. The honest summary is this: the data permit infinity. They do not require it. And more uncomfortably, they may never be able to distinguish between a truly infinite universe and a finite one so large that we can see no edge, no wrap, no seam. This is the deep epistemic limit we touched on earlier in the night, and it bears sitting with. The universe has a finite age, about 13.8 billion years, and light has a finite speed. So there is a horizon, at the particle horizon, the edge of our observable universe, at about 46.5 billion light-years, beyond which we cannot see, have never seen, and, in the strictest sense, can never see. Not because of any engineering limitation we might overcome, because the information from beyond that horizon has not had time to reach us, and as the universe continues expanding, driven by dark energy, that information never will. Whether space continues beyond that horizon is simply not observable from inside. The infinity claim is, in the strict sense of the word, untestable by direct observation. We are reasoning about what must lie beyond a wall we can never see over. This brings us to a problem that physicists have spent years wrestling with and have not yet solved. It is called the measure problem, and it is the kind of problem that sounds like a technicality until you realize it goes all the way down. Remember the logic of the copy argument. In an infinite universe, every possible arrangement of matter must recur, including you. In fact, you recur infinitely many times. Your exact copy exists not once, but an infinite number of times. Your near copies, differing by one atom, one neuron firing differently, one choice made in a different direction, exist infinitely many times each. Every possible configuration consistent with the laws of physics exists infinitely many times. Now ask a simple question. Among all these infinite copies of you, what fraction are, say, left-handed? Or what fraction are reading this sentence by lamplight rather than in darkness? Or what fraction will, when this is finished, drift into a dream rather than lie awake? In a truly infinite universe, every version of you, with the left-handed one, the right-handed one, the one who chose differently at every crossroads of their life, exists infinitely many times. So the fraction that is left-handed is infinity divided by infinity. And infinity divided by infinity is not a number, it is undefined. The answer depends entirely on how you count, and on what mathematicians call the measure you choose. Count copies in one order, and left-handed versions might seem to dominate. Count them in a different order, and right-handed ones seem to. The mathematics doesn't give you a unique answer. This is not a minor quibble. It means that in an infinite universe of this kind, ordinary probability breaks down. You cannot say that this or that outcome is likely or rare. Every outcome happens infinitely often. The statistics become undefined unless you impose an additional rule, a measure specifying how to count. And cosmologists do not agree on what that measure should be, or whether any particular choice is physically meaningful. It is a serious problem. Tegmark knows about it. Guth knows about it. Vilenkin has spent considerable effort trying to address it. None of them claim to have fully solved it. Some critics point to the measure problem as a sign that the infinite universe with copies framework is internally inconsistent, that it destroys the very notion of prediction and therefore of science. And then there is another caveat, quieter, but worth sitting with on a night like this. The popular framing of the copy argument often says something like, right now, somewhere, another you is reading this same sentence at this same moment. And that image is vivid, and I understand its appeal. But it is physically loose in a way that matters. There is no universal now. That is one of the deepest things Einstein gave us. The relativity of simultaneity tells us that what two distant observers call at the same moment depends on their relative motion. Two events that are simultaneous for one observer are not simultaneous for an observer moving relative to the first. At the distances we are talking about, in 10 to the 10 to the 28th meters, or vastly more, there is no meaningful sense in which right now can be coordinated between you and your copy. The phrase "your copy is reading this at the same instant" is, strictly speaking, not well defined across cosmic distances. The copy exists if the universe is infinite. But at this moment is a story we tell ourselves to make the idea feel vivid. The actual physics is stranger and more spacious than that. Now, all of these complications, the unproven infinity, the torus alternative, the measure problem, the fuzzy now, bring us to a group of physicists and thinkers who have raised their hands and said, "Wait, just wait." The most prominent is George Ellis. Ellis is not a fringe figure. He is an eminent cosmologist, a fellow of the Royal Society, and a long-time collaborator of Stephen Hawking. He has spent his career doing serious, rigorous work on general relativity and cosmology. And in August of 2011, he published a piece in Scientific American titled, "Does the Multiverse Really Exist?", in which he laid out a principled, careful objection. Ellis's position is not that the multiverse is wrong. He is explicit about that. His position is that claims about regions beyond our cosmic horizon, including the level 1 multiverse, the most conservative one, the one we've been exploring all night, extrapolate known physics into regimes we can never test, and that calling such claims science, in the traditional sense of a discipline that generates testable predictions and allows itself to be falsified, stretches the term beyond its usual meaning. This is an important distinction. He is not saying the idea is crazy or that Tegmark is a crank. He is saying that this follows if you take the premise at face value is not the same as we have scientific evidence for this. Science, at its best, is distinguished from other ways of knowing by its willingness to be shown wrong. A claim that is in principle unverifiable, that could not possibly be contradicted by any observation, sits in a philosophically awkward place, regardless of how elegant the logic is. Ellis is joined in various degrees of skepticism by others. Paul Steinhardt, a Princeton physicist, who was himself one of the early architects of inflationary cosmology, one of the people who helped build the theoretical structure that makes eternal inflation possible, turned sharply against the multiverse interpretation in later years. In a 2014 piece in Nature, he argued that eternal inflation makes so many predictions simultaneously that it cannot be tested, and he called this a Big Bang blunder, a sign that the theory had drifted from science into something else. Coming from someone who helped build the framework, this is a significant criticism. Sabine Hossenfelder, a theoretical physicist whose 2018 book, Lost in Math, attracted wide attention, has made a broader argument that modern theoretical physics has, in some areas, become too enamored of mathematical elegance and internal consistency at the expense of empirical grounding. The multiverse, beautiful, logical, internally coherent, fits her profile of a theory that physicists find compelling for reasons that may have more to do with aesthetics than with evidence. These are serious people making serious arguments, not a chorus of dismissal, but a thoughtful minority within a field that takes these questions seriously and has not settled them. And here is what I find most striking about the current situation. Tegmark would not disagree with the basic facts in Ellis's critique. He knows the claim is unverifiable by direct observation. He knows it rests on premises we cannot confirm. His response is essentially, we already accept unobservable entities all the time in physics, and the level 1 multiverse is the most conservative one, requiring nothing new, nothing exotic, only taking the math seriously. The copies are implied by physics we already use. Rejecting them requires actively adding an assumption, space stops, that has no observational basis either. Both positions are, in a certain sense, reasonable, and neither has a way to make the other wrong through experiment. Which brings us to the unreachability. And this is perhaps the part that settles into you most quietly, in the dark when the mind is soft and the house is still. Even if you are right, even if the universe is infinite and the cosmological principle holds, and the initial conditions varied widely enough and the copies are genuinely out there, you cannot reach one, you cannot signal one, you cannot ever, in any possible future, learn whether you have a copy or not by direct contact. The nearest exact copy of you is roughly 10 to the 10 to the 28th meters away. Let's not even try to visualize that distance. We established earlier that the unit of measurement, meters, light years, Planck lengths, makes no meaningful difference to the answer. The number is so deep into the double exponential realm that the choice of ruler is noise. But there is more. The universe is expanding, and it is not just expanding, it is expanding at an accelerating rate. In 1998, 3 astronomers, Saul Perlmutter, Brian Schmidt, and Adam Rees, discovered this acceleration by studying distant supernovae, bright enough to see across cosmic distances, close enough in their physics to use as standard candles. The universe was not just stretching, it was stretching faster and faster, driven by something we call dark energy, a name that honestly confesses our ignorance of its nature. They were awarded the Nobel Prize in Physics in 2011 for that discovery. And what dark energy means for your copy is this. Distant regions of the universe are already receding from us faster than light. Not because anything is moving through space faster than light. Nothing does. But because the space between us and those regions is expanding, and the cumulative effect of that expansion across vast distances exceeds the speed of light. The light from those regions will never reach us. We have already lost access to them, cosmologically speaking. So not only is the distance to your copy unimaginably vast, that distance is growing. The gulf between you and any copy is not stable. It is increasing, driven by the accelerating expansion of space itself, and it will never stop increasing. And nothing you could send, no signal, no ship, no light, could ever cross it. The universe is, in a certain beautiful and melancholy sense, actively separating you from every copy that might exist. The most profound consequence of modern cosmology may be permanently beyond experiment, not temporarily, not until we build better instruments, permanently, by construction. Because the structure of space-time itself, the finite speed of light, the finite age of the universe, the accelerating expansion driven by dark energy, places a hard horizon around what can ever be known from inside. And so we arrive at the seesaw. On one side, if the universe is infinite, the copies are not speculation. They are not a colorful possibility or a whimsical extrapolation. They are a near-logical consequence following from the pigeonhole principle and the holographic bound with a force that makes them feel almost like a theorem. The conclusion is stronger than most people expect when they first encounter it. Not probably another you. Infinitely many yous guaranteed with probability 1 under the premise. On the other side, that premise, space is truly, actually infinite, is unproven. It is consistent with the best data we have. It has a plausible theoretical story behind it through eternal inflation. But it cannot be confirmed by observation, ever, from inside the universe. And there is a principled, thoughtful minority of physicists who argue that basing grand conclusions on unverifiable premises is a step away from science and towards something else, not pseudoscience, but perhaps a kind of metaphysics wearing physics clothes, almost a theorem, resting on a maybe. That is the seesaw. And I don't think either side of it is where the real wonder lies. The wonder is in the seesaw itself. The fact that we can reason our way using real instruments, real mathematics, real experiments, a satellite measuring the temperature of the oldest light in the universe to a precision of parts per million, to the edge of a question that is, at its heart, the same question humans have asked since they first lay on their backs and looked up. Is there more? Is there more out there than I can see? Is the universe bigger than my horizon? And we have a real answer now, of sorts. We don't know. But we know the shape of our not knowing more precisely than anyone in history has known it. We know exactly what would have to be true for the copies to exist. We know the geometry of the argument, the assumptions it needs, the physics it draws on. We know what is held within the logic and what is assumed beneath it. That is not nothing. That is, in fact, remarkable. Let me say something about the ancient company we are in. Lucretius, writing in Rome in the 1st century before the Common Era, in his great poem De Rerum Natura, on the nature of things, imagined infinite atoms over infinite space and concluded that other worlds must exist, other versions of every arrangement. He had no instruments, he had no equations. He was working from philosophical first principles and a poet's instinct for consequence, and he arrived at a recognizable ancestor of the argument we have spent this whole night tracing through satellite data and quantum information theory. Giordano Bruno in the 16th century argued for an infinite universe with innumerable worlds, and was burned at the stake in 1600 in Rome for views that threatened the worldview of his time. Not only for the cosmology, it should be said, his case was tangled with theology and other charges, but the infinite universe was among the ideas that made him dangerous. Nietzsche in the 1880s had his own version of eternal recurrence, not in space, but in time. If time is infinite and states are finite, then every configuration of the universe recurs again and again forever, a time-based cousin to the spatial argument. He called it the heaviest thought, the most demanding thing to truly accept. It is not the same as Tegmark's level 1. One is physics, one is philosophy, but they share a family resemblance, and the vertigo they induce is similar. The question of whether there is more, whether the universe has an end, whether we are unique or one of many, it has been with us for as long as there has been a us to ask it. What has changed in the last few decades is that we have instruments precise enough to give the question real teeth. Planck and WMAP have told us what the curvature of space is, to a precision that would have seemed miraculous to Lucretius. Jacob Bekenstein's work on black holes and information has given us a rigorous reason to think that any finite region of space has a finite number of distinguishable states. The holographic principle, developed by 't Hooft and Susskind, has given that intuition a theoretical foundation. Guth and Linde and Vilenkin have given us a detailed mechanism, eternal inflation, by which an infinite universe might have come to be. Cornish and Spergel and Starkman searched the sky for evidence that it wraps around. Perlmutter and Schmidt and Rees showed us that dark energy is pulling everything apart. We didn't have any of that, and now we do. And what it has given us is a question we can state with extraordinary precision, resting on a premise we cannot confirm. If that one syllable carries the weight of everything, if space is truly infinite, if the cosmological principle holds on the largest scales as it seems to on the scales we can observe, if initial conditions varied enough to generate every possible arrangement, then you exist again and again and again, scattered through a space so vast that the number of copies defies any human attempt at comprehension, separated by distances that make the number of atoms in the observable universe look like rounding error. And your near copies, the ones who differ from you by one molecule, one electrical impulse in the brain, one moment of different choice, they exist closer. Not close in any meaningful practical sense, still impossibly, laughably far away. But closer than the perfect copy, infinitely more numerous, every variant on you that physics permits, existing somewhere in the infinite dark, going about their version of this night. Wherever you are right now, whatever room you're lying in, whatever the lamp situation is, whether there's rain on the window or the kind of silence that feels like someone turned the sound off, there may, if the universe is what the logic suggests it might be another version of you in a room just like that, having just spent the night on the same journey, arriving at the same place, or there may not be, and we cannot tell. And that too is part of the picture. I want to close with something that might sound strange, but that I think is actually comforting. The fact that this question sits beyond the reach of direct experiment does not mean the reasoning is wasted. The journey through it, the pigeonhole principle, the Bekenstein bound, the flatness of space, the wrapping topology, the measure problem, the dark energy, the skeptics and the advocates. That journey is a portrait of what human minds can do, of how far reason and instrumentation and mathematical honesty can carry us together, past our own horizon, into questions that may not be answerable in our lifetimes or in any lifetime. And the question itself, is there another me, is not trivial and not silly. It is one of the oldest and deepest things we can ask. It is asking whether we are singular or replicated, whether this particular arrangement of atoms and memories and dreams is unique in all of existence, or whether it is one pattern among infinite repetitions. Whether this night, this room, this slow journey towards sleep is the only one of its kind or one of an infinity. The honest answer is we don't know, but we know that if the universe is truly infinite, and it may be, then this is the only one of its kind is almost certainly wrong. The pigeonhole principle does not care about how you feel about that. Infinite boxes, finite kinds of contents, everything repeats, including you. And if the universe is finite, or even stupendously, incomprehensibly finite, 250 times the observable diameter or far beyond, too large for any seam to be visible to us, then it still contains more than we can see, more than we will ever see. And the question of whether there is another you remains open, resting somewhere in that enormous, unobservable remainder. Either way, the universe is stranger and larger than your anxiety about it. That's the thing to carry into sleep. Back at the start of this long, slow night, we opened with a number, 10 to the 10 to the 28th meters. We said that the units you measure it in don't change it. We said the entire argument rests on a word we cannot yet prove. I hope that by now that number feels different than it did then. Not smaller, obviously. Nothing could make that number smaller, but more earned. You know where it comes from. You know the physics behind it, the assumptions beneath it, the honest people who argue for it, and the honest people who argue it goes too far. You know, the seesaw. And knowing the seesaw is, I think, better than just having the number. The number alone is a parlor trick. The seesaw is the actual shape of our knowledge, almost a theorem resting on a maybe. That is what we know. That is as far as reason and observation have taken us together so far. It's quite far. If you'd like more nights like this one, more slow journeys to the edges of what we know, a like and a subscribe would mean more than you might expect. Small creators like me really do rely on your support to keep these going, and I'd love to know where you are in the world right now. What time is it in your corner of the night? Leave it in the comments if you're still awake enough. If you've already drifted off somewhere in the last few minutes, that's fine. Perfect even. The universe and its possibly infinite copies will still be there when you wake. The question will still be open. The argument will still be almost a theorem. And we will still be here, somewhere in it. Sleep well. Good night, kiddo. Grandpa'll leave the porch light on.